So we will continue today the equilibrium of a rigid body. We have already seen how to do the equilibrium in 2D, and today we will introduce equilibrium in 3 dimensions. Okay, so as in 2D, the first step in solving any equilibrium problem is to draw the free body diagram. The free body diagram represents all forces acting on your rigid body. Okay, and once you do this, you can apply the 2 conditions of equilibrium. Sum of forces equals 0 and sum of moment equals 0. And as we said in 3D, we will have 6 equilibrium equations, 3 in forces and 3 in moments, and then we can solve for up to 6 unknowns. Now, as we did in the case of equilibrium of in 2D, the first step is to know the types of connections. What are the connections we might have in 3 dimensions? Okay, so here we will go over these connections and supports. So first, for the cable, it's like before, the force is always along the cable in a way to have tension. Also here, if you have a smooth surface support, it's the same thing also. I have a force F that is perpendicular to contact. Now here you can see the roller also. This is a roller, you have a wheel. So you have a force also in the perpendicular to contact. So it's like 2D until now. Now what we have these new supports of 3D. First, you have the ball and socket joint. So if they give you the name, you just need to know what type of reactions this reaction will develop. Okay. So if I tell you ball and socket, you should know the figures. You should remember the figure, and this reaction is not permitting any motion in X, Y, and Z. It allows only rotation in all directions. Okay, so if you want, it's like, let's say you have here the point is fixed and you attach to it here this member can rotate. إذا بدكم شوي بيشبه فيتاس السيارة بس فيتاس السيارة فينا نزيحه. Okay, so this is the idea. You can do rotation in all directions, but you cannot move in X and Y and Z. This is why the 3 resistance forces developed in the reaction are Fx, Fy, and Fc. Now, this is a single journal bearing, as you can see in this figure. Okay, always you should think what are the motions that is possible to do. If I have possible motions, then I don't have a reaction. So for example, here, imagine you have here a circular shaft and you can move freely along this direction. So here, if you move your shaft along this direction, you don't have any opposition. And if you rotate your axis about this axis, if you do a couple about this axis, also you don't have opposition because it's a circular shaft. So this is why this reaction, okay, will not develop a force in along the axis and the moment along the axis, but it will have resistance forces and moment in other directions. Because as you can see in this figure, you cannot displace like this. You have opposition, so you have Fx. You cannot displace in Y in Z direction, so also you have a force in Z. The same, you cannot rotate about these 2 axes, so you have a moment coupled along X, and you have a moment along Z resisting moment. Okay. Now, another type of reaction is single journal bearing with square shaft. If I say square shaft, what is the new restriction if I have a square shaft? Who will tell me? If you have a square shaft, can you rotate about the axis?
No.
No. So
No, we can't.
okay, you can only do what here in this figure? You can only displace in this direction. Okay, so what can you say? You can say I don't have a resisting force in this direction, but I have a resisting moment because I cannot rotate. So you will add to the previous case with a circular shaft. When you have a square shaft, you will add a resisting moment in this direction. Okay? And in X and Z, as in the previous case, I cannot displace, I cannot rotate. This is why I have a resisting force and a resisting moment. Okay? Now, let us continue with the types of reaction in 3D. Now, what is the single thrust bearing? In this bearing, you have like a locking effect. The locking effect prevents translation. Okay, so because you have this locking effect and you cannot do translation, you can only have rotation. Then you should add to the reaction in Z and X. You should add the Fy resistance because the locking effect will not allow the translation along this direction. Now, a single smooth pen, okay? If you look at this figure, this is your pen. What is the only motion you can do in this case?
Rotating.
What can I do here for this figure? I can do rotation about this axis here, okay? So I can rotate about this axis. My member can rotate about the pen in the Z direction. Okay, or here they call it, they choose to name it X, in X direction. Okay, this is why I will not develop a resistance moment along X, but I will develop a resisting force Fx. Okay, and in Y and Z I cannot do anything. So here, if you take these two axes, you cannot rotate about them, and you cannot displace your member. So your member is only allowed to do rotation about this axis. This is why the only direction, the only, if you want, allowable motion is rotation about X. This is why we don't have MX. But all other types of motion are not allowed. So I should have resistance, Fy My, Fz Mz, and Fx. Now, concerning the single hinge. The single hinge is like the reaction for doors, okay? You can see it for doors. And here also, the only allowable motion is what? Is rotation about this axis, the axis of the hinge. So the door can rotate about the axis. This is why if you observe here, the only missing reaction is moment about Y, while we have all other reactions, Fy, Fx, Mx, and Fz, Mz. And the final type of reaction is the fixity, like in 2D, fixed support. If you have a fixed support here, which have the symbol like this, I cannot do anything. I cannot translate, I cannot rotate. This is why I will have 6 unknowns of X, reaction in X, reaction in Y, reaction in Z forces, and also reaction moments in X, Y, and Z. Okay? So these are the different types of supports that you can encounter in 3D. And you should be familiar with their figure. So if you see the figure in a problem, you will know that it will develop the following types of reactions. Now, the second step, once we know the type of supports, then the second step is to apply the equilibrium conditions on the rigid body. So as we said previously, we have two vectorial relations to satisfy. Sum of forces equals 0 first, like we did for the particle, but we should add to this equation an equation for the moment, which is sum of moments equals to 0. Okay? And when we do sum of moments, we should consider all forces moments, so it's some are vectorial F, but I want also to add something here. We should add plus moment of couples, okay? Plus sum of moment of couples. So if you have couple moments, you should add them also. Okay. Now, in some cases, we may have more support than are required for equilibrium, whereas in other cases, we don't have enough support for equilibrium. What do we mean by this? We have two cases here, redundant constraints and improper or partial constraints. What do we mean by this? First, what is redundant constraints? I will give you an example. If you have a beam in 2 dimensions, and if you put 2 pins, okay, instead of 1 pin, 1 roller, if you decide to put 2 pins, what are your reaction developed? If you have a pin, you have a force in X and you have a force in Y. So let us say here, let's say you have here AX, AY, and here you have BX, BY. So how many unknowns do you have here? You have 4 unknowns, and you have only in 2D equilibrium, you have 3 equations. So your equations are not enough to solve for your unknowns. In this case, we say we have more supports than needed. So we have equilibrium, but we cannot calculate the reactions. And you will see after, for example, if you take mechanics of materials, that you can use an additional equation from, not from statics, okay, from mechanics of materials, for example, to determine these reactions. So by using just statics, equilibrium, you cannot find the 4 unknowns because you can only write 3 equilibrium equations, okay? Of course, 3 equations that are not repeated. You can write 100 statics, infinity of statics equation. So if you choose 100 points, you will say some of moment about A equals 0, some of moment about B, about C, about D equals 0. But at the end, only 3 equations will be independent, okay? Now, the second type is improper or partial constraints. What do we mean by this? For example, if I give you this beam and I put only 2 rollers, I don't put a pin, okay? Then in this case, I will have only forces in AY and BY, okay? This is called partial constraints because in this case, for example, if I put a force in X direction, can my system oppose this force?
No, it cannot.
No, it cannot. It will only be able to oppose the forces in Y, but it cannot oppose a force in X. So it's a partial constraint system. Okay, so I might have, in some conditions, equilibrium can be not satisfied. And improper constraints means that, for example, if I add a roller, okay, I added the number of reactions. I have now 3 reactions, but it's improper because I need an X component. I don't need a third roller like this. It will not help me. What can I do, for example, here? I can put, let's say, I should put a pin. Okay, I should put 1 roller, 1 pin. This will be good. So the good scenario here will be the following. This is the good scenario. Proper constraints is to consider a roller and a pin. In this case, I have only 3 unknowns, and also these 3 unknowns can oppose any possible loading. Okay, so if I put in Y or I put in X, my system can oppose the loading. Okay, because I have here the roller will develop a force in Y, but the pin will develop a force in Y and X. Okay. Now, so for redundant constraints, as we said, okay, the problem cannot be statically solved because we have more unknowns than equations. So this is an example as I gave you. we give 2 pins on for a structure. So we have 4 unknowns, but only 3 equations. So we cannot solve it using statics. And here are examples of partial constraints as we did together. If we put 2 rollers also, rollers will not be able to oppose any force in X, so it's not convenient for all types of loading. Now, let us do together an example. What I want to tell you, when you have partial constraints, you can have, in some cases, equilibrium, but not in all cases. Because I repeat, where, for example, when I give you the example of the beam with 2 rollers, okay? If you only have force in Y, you will have equilibrium, and you can solve for it by statics, okay? So if we have improper if you want lack of reactions, it doesn't mean that I don't have equilibrium. I can have equilibrium, but not in all cases. So here, for example, if I just put a load in Y, I can have equilibrium because the 2 rollers can resist this force. But if I give you a problem with X component, then you will tell me impossible to have equilibrium. So always when you have the number of reaction less than the number of equation, you should study if it is possible to have equilibrium or not. So this is an example here, okay? In this example, rod AB is subjected to the 200 Newton force. Determine the reaction at the ball and socket joint and the tension in cables BD and BE. So as you can see in this figure, you have a member ABC. It's connected to 2 cables and connected to reaction at A. And I told you that the reaction at A is a ball and socket joint. But also, if you look at the figure, you can remember the figure we have in the previous slides. Okay, so here, this type of reactions allows you to rotate in all directions. So it will only develop force forces in X, Y, and Z. Okay. So now if I take the free body diagram of my bar, I will put the forces. I have AX parallel to X axis. I have AY and I have AZ. The other reactions are in cables. Remember that a cable is always in tension. So, for example, for BE, the bar is doing on BE in action like this, okay? So by action reaction, the cable will pull it to this side, okay? So always when you put the force of the cable on the bar, it's directed from the bar towards the cable. So the same for cable BD. So as you can see, how many reactions I have? I have 5 reactions. So here I should pay attention. I might have equilibrium, but I might not. Because in 3D, how many components reaction I should have in general to be on the safe side? Okay, I should have 6 proper reactions. Okay, now here, let us see, we might have equilibrium, as in the example I give you here, for example. If I have only Y, I have equilibrium even if I have only 2 rolls. So we should investigate if equilibrium is possible or not. We will see how. Now, what are other forces acting on my bar? I have the weight of my bar, which is equal to 200 Newton. So now I will put my forces. I will annotate them. I have AX, AY, and AZ. Okay. So now, the step is like in particles. Same, we follow a certain methodology. The first equation we write is that sum of forces as vectors is equal to 0. Of course, 0 vector. Okay. So as you did for equilibrium of a particle, the first step you express all your forces in NIJK system. So to start by the resistance force. So for the resistance force at A, since it's a ball and socket joint, So it has components along X, Y, and Z. And I named them AX. So it's AXI plus AYJ plus AZ plus AZK. Okay. Now, for the weight, I know completely, I know everything about the weight. It's vertical downward of magnitude 200 Newton. So for the weight, W is equal to minus 200 ln K. And I still have the tension forces. As you can see in the figure, the tensions here are simple. Their unit vector are simple. Why? Because look, TBE is parallel to x-axis, okay? And TBD is parallel to y-axis. So here I don't have a problem with unit vectors. I can just directly say that force TBD vector, okay, is equal to TBD magnitude times what? Times J, because it's along Y. And for my second force, TBE, I can say that TBE vector is equal to the magnitude of TBE times I. Okay, so now I am ready to start my equilibrium equation. The first equation I will write is sum of x equals 0. So I start by sum of fx equals to 0. What do I have along x? RA has a component along x, so AX. The weight doesn't have a component along x. I have TBD is along y and TBE along I, so I have plus TBE equals to 0. Okay, this is my first equation, equation number 1. Now, second equation is sum of fy equals to 0. If I look at my figure, what are forces along y? So first, for RA, it has a y component, so it's AY. For the weight, no y component. For the tension, I have TBD, so it's plus TBD equals to 0. This is my equation number 2. Now my third equation is along Z. Sum of forces along Z equals to 0. So I will write that AZ, and I have the weight, which is minus 200, equals to 0. This is equation number 3. From equation number 3, I deduce that so AZ is equal to 200. So now I just found AZ. I still have a X, a Y, TBE, and TBD. So 4 unknowns, but only 2 equations. This is why it's not enough, of course. I should move to the second condition of equilibrium, which is sum of moments about any point you want. You can choose any point in the figure, but always try to choose the easiest point. Here, what is the easiest point to do sum of moment about?
About A.
About A, very good. Why? Because if you choose to do sum of moment about A, the moments of AX, AY, and AZ will cancel out. Okay? So sum of moments about A equals to 0. Okay? Now, what are forces producing moments about A? We said that for the reaction at A, no moment for the reaction at A. We still have the moment of the weight, the moment of TBE, and the moment of TBD. And remember what I told you, when you have 3D application in general, it is the easier way to do the moment is to do the vectorial product, okay? So I want to find the moment of P of the weight W, the moment of W about A, plus the moment of TBD about A, plus the moment of TBE about A. Okay, this is equal to 0. Now, how we get the expression of the moment? As we said, it's R vectorial F. Okay, so for the weight is passing by C. So I do AC vectorial the weight. And for TBE, I do AB vectorial TBE. And for TBD, I do AB vectorial TBD. Okay, so I will write it here. So I have first AC vector vectorial vectorial the weight, okay, W, plus AB vectorial TBD. Of course, all of these are vectors, okay, plus AB vectorial TBE. Now, if you want to simplify, I can take AB into factor for TBD and TBE. So what do I get? I will replace. Now, I have AC vectorial, I will replace W by its value. It's minus 200K plus, I will take AB into factor, AB vectorial TBD vector, and TBD vector is what? Is TBD magnitude times J, okay? Plus TBE vector, which is TBE magnitude times I, okay? So this is the expression that I want to find. Now, the next step is to find vectors AC and AB, okay? So here, just do not confuse, all of these are vectors. AC vectorial W plus AB vectorial TBD plus AB vectorial TBE. Okay? Now, the next step is to find vectors AC, AB, and AB. Okay? So let us look together at the figure. We should find the coordinates. First, as you can see, for point A, it's on the axis, and we have that the distance from here to here okay, it seems that they okay, so here look, what they did in the problem here, they gave you the coordinates of C and B with respect to which frame. They considered that the origin is at A, because look, they told you, they gave us, even if you want, they gave us the coordinates of this point and this one, okay? So no need to do anything here, because they already gave us coordinates of C and B relative to A. So A is the origin. So for A, I have 0, 0, 0, okay? Now, for point B, they told me that it's 2, 2 minus 1, okay? And for point C, you can find it easily. They gave it to us, but we can find it easily because C is at the middle of AB. So x of C is x of A plus x of B over 2, etc. So they gave us that C is 1, 1 minus 0.5. So we know the coordinates. The coordinates are given in the problem, okay? If they don't want to give us the coordinates, they can just tell us that this distance is 1, and we can continue, okay? Because look, you have B, for B, the coordinates are clear. You have 2 along Y, you have 2, sorry, this is along X. So you have 2 along X, you have 2 along Y, and it is, so if they give us that the distance here is 1, and we take that A is the origin, B is below A for a distance of 1. So it's 2, 2 minus 1. Now, since as you can see in the figure, C is at the middle of AB, so you can easily find coordinates of C by saying that x of C is equal to x of A plus x of B over 2, y of C equals y of A plus y of B over 2, etc. Okay, so now I know coordinates of all my points. Then I can find the vectors I am interested in. I am interested in finding AC and AB. So of course, vector AC is simply, since A is the origin, vector AC is equal to I plus J minus 0.5. Okay, and for AB vector, so also I just consider the coordinates of B since A is the origin. So it's 2I plus 2J minus 1 minus K. Okay, so now I am ready to replace into sum of moments. So if I go back to my relation, I want to find sum of moments about A. So I have first AC vectorial weight. I replace AC by its value, which is I plus J minus 0.5 K. Vectorial, the weight, which is minus 200 K. Plus AB, I replace AB vector by its expression. AB is 2I plus 2J minus K. Vectorial, as we said, TBE plus TBD, okay? So it's TBD, it's TBD J, okay? Plus TBE I plus TBE I, okay? Now what should I do? I should do the expansion, okay? This is equal to 0, so it's 0I plus 0J plus 0K, okay? Now I will expand the first side. Now, if you remember, when we introduced the vectorial product, we have several methods to calculate. Or you use the matrix method, or here, because it's simple, here you have only one term, so you can do expansion. It's easier than doing the matrix. So I will start to say I vectorial K. It's what in my head I say I, J, K, I. Ki is positive, so Ik is negative. I vectorial K is minus J, and already I have a minus, so it's plus 200 J. And if you don't like the method in your head, you can just draw a circle like this and say I will turn in a certain positive direction, and I will put here I, J, K. Okay, now look, if I do K vectorial I move in the positive direction. If I do I vectorial K, I'm moving in the negative direction, so it's minus J. Okay, and already I have a minus, so it's plus 200 J. Now, J vectorial K, if I look at the figure, J vectorial K is positive, but I have a minus, so minus 200 I minus 200 I. And of course, K vectorial K is what? Is 0. Okay? Plus, for the other term now, here if you want, because it's little bit more complex, let us do together the matrix method here, because you have a lot of terms. So if you want to use the matrix method to get this vectorial product, I will remember you of the technique. So we put the matrix. For the first line, we put I, J, and K, For the second line, we put the coordinates of the first vector, which are 2, 2, and -1. Okay. Now, I have here the second vector. We have TBE along I, and we have TBD along J, and we don't have anything along K, so 0. Okay. Now, if I want to do the development, if you remember, we put plus, minus, and plus, and we start to do the expansion. Okay. So I will write here, I have plus I. For I term, what do? I drop these two. I have 2 times 0, which is 0, minus TBD, so plus TBD. So along I just have TBD. Now along J, I put minus J times. I have 2 times 0, okay, minus TBE, so plus TBE, and finally along K, so plus K times, I drop these two. I have 2 TBD minus 2 TBE, so 2 TBD minus 2 TBE. Okay, and now I am done with the expansion of this term. This is along K equals to 0I plus 0J plus 0K. And now what is the final step? The final step is to compare the two sides along I, J, and K. Okay, and we will obtain 3 equations. So we will say, by comparison, along I. What do we get when we compare along I? From this side, we have minus 200I, minus 200, and we have plus TBD equals to 0. This is equation number 4. And from equation number 4, we get that TBD is equal to 200. Okay. Now, when we do comparison along J, what the comparison will give us? Plus 200 minus TBE equals to 0. This is equation number 5. And I get from this relation that TBE is equal to 200. And finally, if I consider along K, if I compare along K, what do I get? I get that 2 TBE minus 2 TBD, okay, equals to 0. So from this relation, I get that TBD equals to TBE. But I already know this. From the previous calculation, I already know this. Why here I have a repetition of the result? Because as I told you, in this problem, you have only 5 unknowns, but you have